So in this video, we will discuss coordinate system and positioning. So it is expected at the end of this lesson that the student should be able to identify basic positioning modes used in modern geodesy and the different coordinate systems. So here are the contents of this lesson. So first we have the coordinate system and reference model, and second we have the positioning in geodesy. So when we say coordinate system, so what are the system used in uh, identifying position of your spatial data or points? And in positioning, what are the methods or common methods used today in geodesy? So position is defined at least two or three quantities. So let's say two or three in our Cartesian system, we have x and y, or in surveying, we have northing and eastings. So in geodesy, there are several coordinate systems being used from which the position of a point on the surface of the Earth is being referred. So since we have these quantities, so they are called as coordinates. No? So coordinates, uh, it is equals to x and y. Then you have your position of your point. Uh, so if in space or 3D, so x, y, and z. So again, the coordinates of a certain point is referred to a defined coordinate system. So if we don't have a system, then these coordinates will be useless. No? So somehow they are referred to an origin or reference. Okay. So this will answer like this question, no? With respect to what? So what are you referring to? No? So you have your point, you have your, let's say, you have your uh, ground control point, GCP. So this point has a coordinates, let's say on 10,000 by 23,000, northings, eastings. So you have, it has known coordinates, but with respect to what? No? It should be defined. Not only the coordinates, but where the coordinates referred to. No? So that's why we have a what we call coordinate system. So as a matter of convention, we have two kinds of points or data or spatial data as they say. No? So first we have absolute, which are taken to be with respect to a defined coordinate system. So meaning to say, um, if let it let us put this way, so we have your Cartesian. So when we say absolute, so you have your point here with known coordinates. So what we did here is uh, this is your reference system and this is your point. So that is an absolute point, no? So absolute point, which is uh, with respect to your reference system. So this is your origin. Okay. So when we say relative point data, so they are taken to be the difference between the two absolute values in the same system. So for example, you have another one, say x sub s, y sub s. So they are relative to each other. So that's the same with surveying, let's say in property survey. So when we establish new corners or when we conduct survey, we always refer our survey from a known reference position or reference control point or uh, reference ground control point or GCP, which is your GCP is attached or defined from the or from a certain coordinate system. For this one, when we say relative, you refer your position from a known reference point, no? Okay? Or somehow their difference in coordinates, no? Okay? So we have two general types of coordinate systems. So we have the parameters. So first we have the rectilinear type of coordinate, and we have the curvilinear type of coordinate system. So when we say rectilinear, they are orthogonal, straight line, no? So common example for this is the Cartesian coordinate system and the curvilinear. So we have the angular measurements, and the third attribute is the height. So that serves the linear. So when we say curvilinear, di ba, we have this latitude, longitude, and height as shown in this image. Okay. So in terms of surface or space dimension, so we have linear, planar, and space. So when we say linear, so a common example for that is distance measurement. Then for planar, 2D positioning, no? Two-dimensional positioning. So we have in surveying, we usually use northing and eastings or x and y in Cartesian plane. So in space 3D, we have this um, northings, eastings, and up. So up means you do vertical. So this is by means of local projection, or global projection. We have x, y, and z. So as shown in this image. So you have your x, y, and z. Okay. So there should be fine definition between the local projection and global, which will be discussed also in this video. So the positioning in geodesy is concerned to the three-dimensional surface of the Earth. So since geodesy considers the curvature or surface of the Earth, no, so it is essential to consider three-dimensional positioning or the three-dimensional surface. So from this, it can be represented in two-dimensional or three-dimensional geodetic models. So here are the coordinate systems used in geometric geodesy. So first, we have the Cartesian. Second, we have the geodetic coordinate system. And the third one, we have the local coordinate system. Though Mop-Grid can be considered separate, but we will also include it in this discussion. So first, we have the Cartesian coordinate system. So its properties, no, it's a rectilinear type of coordinate system in 3D surface. So as defined by the National Geospatial Intelligence Agency, it is an Earth-centered, Earth-fixed rectangular coordinate or rectangular Cartesian coordinate system. So ECEF, Earth-centered, Earth-fixed rectangular coordinate system. So as shown here. in this figure. Okay, so it's a right-handed coordinate system. Diba? You use your right hand, your thumb, your uh, index, and middle finger. No, so the thumb serves as your z-axis, your index serves as your x-axis, and y serves as your, or the middle finger serves as your y-axis. So that's the mathematical representation of the right-handed coordinate system, of the Cartesian coordinate system. So the origin at the is at the center of mass of the Earth. So here it is 0, 0, 0. So, and it is also defined that xy plane is coincident with the equator as shown in this figure, and the z-axis is defined by the location of the conventional terrestrial pole. So, as an example, we have also the CTP and CIO as discussed in our previous lesson. So, to define position of a point in this space, no, or in this system, so XYZ is used as its components, no, or coordinate components. Okay, so as shown here, so it has its coordinates, so XYZ. Okay, so with respect to X, no, so you have your uh, X here. So from this to this X, then for Y, you have your Y, and for Z, from here to here, so that's your Z. So that's how we locate positions in three-dimensional Cartesian coordinate system. Okay. So for the next one, we have the geodetic coordinate system. So it is used to reference points or spatial data by geodetic position on the ellipsoid. So this system is a curvilinear type of coordinate system on 3D space. So we have the following parameters, no? So as defined by angular units. So somehow we define it uh, by degree minute seconds, no? So we have the latitude. So for latitude, uh, or for the latitude, positive latitude, that is going north, and for locations from the equator going south in direction, that is negative in latitude. And for the longitude, from your Greenwich meridian going east, that is positive longitude, and going west is west in direction, that is negative in longitude. And we have also the third element or dimension, which is the ellipsoidal height, as shown in this figure. So we have your uh, position, or I mean distance h. So when say distance h, that is from the surface of the ellipsoid to the point. So this distance should be, or I mean this line from the point going to the ellipsoidal surface, this height is normal to the surface of the ellipsoid. Okay, so that's why uh, we have this from this point, from the surface of the ellipsoid going to the inside of the ellipsoid. So you have your radius of curvature. Okay. So lines of equal latitude are called parallels, and lines of equal longitude are called meridians. So other term for this system, no, for the components. So when we say geodetic coordinate system, we can call it also geodetic latitude and geodetic longitude. Okay. So next we have the local coordinate system. So for this one, it is the origin. Let's say origin is defined by user, or they are arbitrarily chosen. No? So in local coordinate system, as uh, as the title says, so it is in local, meaning to say limited, limited coverage, and curvature is somehow uh, neglected. No, curvature is not considered. So it's a planar representation of the surface. So somehow, as shown in this image, no. So this is the surface, no. So as you go further from the origin, no, tendency, you have your separation, no. So you have your separation, so that will cause distortion, and also um, distortion also for the data. For example, if you have some data that will be taken on this part, no. Okay, so anyway, we will not talk about distortion because this is already discussed in your cartography, no, or map projection. Anyway, so for the local coordinate system, it portrays the location of points, spatial data with respect to an origin, so such as this one. Okay, so it's still a three-dimensional system. Okay, as shown here. So you have your usually eastings is x, northings is y, and up is z. But for this one, to make it simpler, so you have your, for example, this is your region, this is your point. So this point is somehow above on this plane. Okay, so you have your plane. So you have your point here. Okay, so from this perspective, it has shown difference, no? Difference in eastings, difference in northings, and difference in up component. So from this one, this is somehow what we call relative positioning. So you have your delta. For example, if this origin is known, then we can compute its position of this unknown point, given that we already knew the delta, the unknown. Then from that one, we can compute your slope distance, right? So when we compute your slope distance, so that will be equals to square root of delta E squared plus delta N squared and delta U squared. Okay, then that you will have your slope distance, as well as for the vertical or zenith angle. You use the up component and the what and this distance, okay, horizontal distance. So for the horizontal distance, that would be equals to square root of, okay, so that's how you compute for your horizontal distance and your slope distance. And also for azimuth, you can compute also your azimuth, given that you already have your difference in eastings and difference in northings. Okay, so again, we have the three components as shown here. So that we have the east, north, and up components. So in this perspective, when you perform a survey, when your traverse is already oriented, no? So it's easy for you to identify where the location. For example, you are given a such coordinates and you are standing from a known point or position. So from there, you will already or you can already visualize where the point is because you are already oriented, but in a local sense. Okay? So, but the difference with the other two mentioned or discussed coordinate system. So let's say we have XYZ or 3D Cartesian or the Cartesian coordinate system. If you are given XYZ of such point and you are standing on a known position with XYZ coordinates, you'll be having a hard time where to locate that point because um, you're not standing on a origin. No, the representation is not with respect to your position. Okay. The same with the um, geodetic coordinate system. So you're standing on a known position, let's say latitude and longitude, and you have this position given na you want to identify or you want to locate with a certain uh, with a certain latitude and longitude position. So in a sense of given that you are oriented, no, you are facing north, you are facing certain direction, there's a chance you can locate that point. Not the same with the Cartesian because the origin of that point is with respect to the center of the Earth. However, for the local coordinate system, as I said lately, you can able to locate such position with an ease because the origin is from your position, given that your um, orientation is already oriented. No, okay. So that's the difference between the three coordinate systems. In terms of self, let's say you want to locate such point, no. But in terms of global coverage, it's easier to use the Cartesian and the Geodetic coordinate system because local coordinate system is only used or it is assumed that the location of a limited area as flat. Okay, so when we talk about global sense, we cannot consider such positioning of a certain surface or point as flat. No. Okay. So we have additional one. We have the Mop-Grid coordinate system. So shown here, we have the Mercator projection. No, that means turning the curved surface to a flat projection by means of mathematical transformation or map projection. So this is a rectilinear type of coordinate system on a planar surface. Okay, so that's why um, when you try to project surface on a flat sheet, tendency there will be distortion such as this one. Okay, so this should be somehow in a form of grid, but somehow it is elongated. So in the Philippines, we have less distortion because um, we are here, no? So we are not far away from the surface, not unlike here. So if we project this one to a paper, when we elongate this one, so that's why it is stretched, it is distorted, no, from the surface going to that one. So that's why it is distorted, which means that the true shape of the, let's say when you are asked what is the true shape of Brazil or true shape of the Philippines. So technically, if we can go out in outer space, so that's the perfect one. No, we cannot replicate a perfect one, no, because of the distortion. However, we can be closely accurate in producing maps, but in terms of perfection, there's nothing more perfect with the Earth. No, so all you need is we need to ride a rocket and go out to space. So in the parameters in defining points here is by northings and eastings. And also, we can also define it uh, in latitude and longitude. No? So when we say latitude, so from equator going up, that is positive latitude, and from equator going down, that is negative latitude. So from Greenwich, so not shown here, somewhere here, Greenwich. Where is the Greenwich? This one. So you have your zero longitude. So going east is positive longitude, and going west is negative longitude. Okay. So this is your Greenwich meridian. Okay. So by that, we can also locate your points in two-dimensional space. Okay. Or other terms, we have the northings and eastings. Okay. So for this one, the elevation component will serve as an attribute to this coordinate system, no? Because this is flat. So for example, you have your point here, it has corresponding coordinate system, and you can only attribute its elevation. Let's say elevation is 10 meters. So that's how you define its position and adding its elevation component. So here are the positioning modes in Geodesy. So each positioning mode can be done using one or more surveying operations or method by terrestrial, celestial, or orbital platform. So before we have this point positioning. So it is the determination of the coordinates of points based on a fixed object not lying on the terrestrial surface. So before we have this um, kind of positioning, no, we use the stars or heavenly bodies, no, as our reference. So that's why we have your celestial reference system. Okay. So from this one, we utilize stars or the sun as our reference. No. So we utilize them, we observe them in order for us uh, to to define our position. Okay. So from that one, we can determine our position such as the astronomical latitude, and longitude. Okay, so once we already define this one, then you have your position. So that is with respect to the uh, stars or astronomical sense. Okay, so this is before. So with the advent of global navigation satellite system, so we have the relative positioning. Okay, so it is the determination of the coordinates of points with respect to an existing points. So such as this one. So you have your A, B, station A and B. So you want to determine station C. Before uh, they perform triangulation, right? So triangulation, trilateration, or and traverse. So these are the methods employed before in establishing control. So this is somehow what we call relative positioning because you refer your coordinates of point C with respect to the known stations. It could be A or B. So or both, no? Just to make this uh, identification or determination stronger, no? So you have this figure, then they employ strength of figure, or the method in establishing point C can be also combined. Triangulation by angles, trilateration by distance, and traversing both mix. Okay, so there you have it. Okay, then once you reach point C, you perform the strength of figure, you perform the adjustments, the network, I mean the traverse or the figure adjustment. Then if the accuracy is accepted, then you can determine point C. So that's how tedious they perform this kind of surveying. So with the advent of the global navigation satellite system, so relative positioning uh, made easier, not only easier, but also the accuracy is also improved. No, this is especially when we perform measurements um, far from the reference point. Let's say you have a mountain there. Okay, you have a mountain there, so you can still perform positioning on the other side, no? Because we have this satellites serves as your reference point, no? So instead we use heavenly bodies as our reference. Now we move to the satellites, which are artificially made by humans and sent to space, and they are precisely um, monitored and also provides good positioning to the user. But for today, stars are also or still being observed because they serve as our ultimate reference in 3D space. No? Only that we utilize GNSS in order for us uh, to make measurement faster, easier, and will not suffice the accuracy. Okay. So in kinematic positioning, this is more also preferred in Geodesy. So this is used in navigation. So when we say navigation, it can be aircraft, uh, terrestrial, you have your cars, and also in naval or ships. Okay, so they are used mainly in aircraft, terrestrial and naval ships, but also it is used in surveying. No, so this kind of positioning is positioning of moving objects. So it is a real-time positioning, meaning to say real time at that instant you will know your position. No, although when we the difference between static is not moving, and kinematic moving, this is still accurate. No, and this is also accurate. Let's say when we talk about millimeter accuracy, here we have centimeter or millimeter accuracy. No? Only that in static, the observation time is longer. And for the kinematic, the observation time is short or real time. So I'm referring to the global navigation satellite system mode of positioning. Okay, so yeah, so as you stand here, you have your position, and when you move, it is real time. Uh, or your position at this instant is also determined in real time. So uh, that's the advantage in kinematic positioning using global navigation satellite system. So at that instant, you will have your position. Okay. So as a summary, no, we already discussed different coordinate system used in geodesy. So uh, we have the Cartesian, we have the Geodetic coordinate system, and we have the local coordinate system. So each of them has advantages, and each of them has disadvantages, no, in terms of uh, positioning. Okay, so whether if in global sense we utilize more on the Geodetic or Cartesian, in local sense, so we use the local coordinate system. Okay, so from this one, we have also mentioned or discussed the positioning modes in determining position of a certain point or a spatial data. So we have three kinds of positioning discussed. So most likely used today in Geodesy is we have the GNSS or Global Navigation Satellite System using its modes or techniques such as the static one and the um, kinematic positioning, which provides real-time solution, which is a common or which is a advantage in the science of geodesy. And to make it to end this lesson, positioning of points is essential in geodesy. Okay, so I hope you got some ideas and knowledge in this lesson. So here are the reference used in this lesson, and see you again in our next meeting.